Cross entropy is a very important topic that we discussed earlier in the context of a binary dataset. It is an important tool that allows us to distinguish between a good model and a bad one. Cross entropy is a method of measuring error within a neural network, and consequently a lower cross entropy value implies a more accurate system, while a higher cross entropy value implies a less accurate system. The previous formula that we discovered for cross entropy was the following. This formula applies to a binary dataset, where we have some number of points m. Recall that ultimately, what this equation did was take the ln of the probability of the points being in the positive region, which was then added to the ln of the probability of the points being in the negative region. We did that for every single point, then took the negative to obtain the total cross entropy. If you're not familiar with this equation, make sure to refer back to the neural network section since we've implemented it into our code. Anyways, the larger the cross entropy value, the larger the error, the less accurate our model was, and vice versa. Multi-class cross entropy functions the same way, in the sense that it still provides us a tool for measuring the performance of our network. The same concept applies even if we're dealing with many classes. The larger cross entropy, the larger the error. Let us refer back to our sports ball type example to help explain just how multi-class cross entropy is calculated. You first begin with a certain number of data points. For this example, let's choose 3 arbitrary data points. Let's assume we have 3 unidentified balls, each one with some input of size, weight, color, and texture. What we'll do is pass the inputs of each ball into our neural network. First, we pass in the inputs of the soccer ball, and the neural network determines it has a 40% probability of it being a soccer ball, a 20% probability of it being a basketball, and a 40% chance of it being a volleyball, which isn't very accurate. Then we pass in the inputs of the basketball, and the neural network determines it has a 30% chance of being a soccer ball, a 60% chance of being a basketball, and a 10% chance of being a volleyball. This prediction is somewhat accurate since it assigns the higher likeliness towards it being a basketball. And finally, the volleyball, passing its inputs into the neural network predicts its likeliness of it being 50% a soccer ball, 30% a basketball, and 20% a volleyball. Let's plot our results onto a table. These are just tabulated values that the neural network predicted. Now ball 1, ball 2, and ball 3 have already been labeled. They've already been one-hot encoded as being a soccer ball, basketball, or volleyball. Although our neural network, the current model, predicts that ball 1 only has a 40% chance of being a soccer ball, ball 2 only has a 60% chance of being a basketball, and ball 3 a 20% chance of being a volleyball. Clearly, the current neural network is inaccurate. The model misclassified our data. Whatever model we're using, it has a large error. We must calculate the total error and thus calculate the cross entropy for this specific set of data. Just like how we did it for binary classification, we simply take the natural logarithm of the probability of each data sample being what it actually is. Our first ball, which is already labeled as a soccer ball, its probability of actually being a soccer ball according to our neural network is 0.4. So we'll take the ln of that. Our second ball, already labeled as a basketball, its predicted probability of actually being a basketball according to our neural network is 0.6, so we'll take the ln of that, and do the same thing for the labeled volleyball. We'll take the ln of 0.2, the ln of the prediction of it actually being a volleyball according to our model. We'll add everything up, and don't forget we always take the negative, and thus obtain a cross entropy of 3.04. And just like before, the higher the cross entropy value, the higher the error. This is very similar to how we did it for binary classification, except now instead of using binary cross entropy, we're making use of categorical cross entropy. This was our equation for binary cross entropy. Our categorical cross entropy equation is a little bit different. Having calculated the cross entropy for this set of data, let's actually generalize categorical cross entropy into an actual formula like we did here for binary. What we'll do is first convert our probabilities into variables. The variables here represent the events, the predictions made by the neural network on each ball being a soccer ball, a basketball, or a volleyball. In order to calculate a general formula for the cross entropy, we must recognize the steps we took to calculate the cross entropy in our specific case above. We'll represent the row as I and the columns j. This makes sense if you think of this as a matrix with the rows and columns. The axis traversing the rows is often denoted as I, whereas the axis traversing the columns is often denoted as j. Anyways, we add the ln of each prediction in all of the cells in the first columns, and multiply each row by the event of whether or not something is true. An event that's true will have a value of 1, while an event that does not occur will have a value of 0. So if we were to draw another table, we'd end up with the following. The first ball is already labeled as a soccer ball. It's been one-hot encoded as a soccer ball, such that it has a value of 1, 0, 0. The first event is true, it does occur. We know this ball is a soccer ball, it's not a basketball or a volleyball. This one is not a soccer ball, nor is it a volleyball, this one is a basketball, so it's one-hot encoded as 0, 1, 0, and the same concept applies to the volleyball. It's one-hot encoded as 0, 0, 1. So what we do is we take the ln of each prediction, multiply it by the event of it occurring or not, giving us the cross entropy for a single ball. But notice the other two values cancel out, which is exactly the point. Thanks to the one-hot encoded label, it cancels out two cells, and for the first ball, takes the probability of the ball being what it actually is. Then we do the same thing for the second column. Notice the first and third value cancels out, thus only taking the ln of the probability of the second ball being what it actually is, a basketball. And the same thing for the third column. The first and second value cancel out, and then we end up adding everything up along the axis I. The next step is to then take the negative and thus obtaining the total cross entropy. We know P11 was initially 0.4, P22 was 0.6, P33 was initially 0.2, and would you look at that, we get the same equation as before with the same result, 3.04. And that will be the formula for multi-class cross entropy. As mentioned earlier, the smaller the cross entropy value, the better the model, so we then use some sort of gradient descent algorithm to minimize the error obtained. It is also important to mention that the process of gradient descent and the process of backpropagation are both not generally affected by shifting the analysis of a binary dataset to a multi-class dataset. We're still trying to minimize the error by updating our linear parameters based on the gradient of our error function.